So I want to take the Fourier transform of this function, so x squared plus 2 over x to the fourth plus 4, and I want to do that using the residue theorem. So first, again, I will try to find the poles, so the regions where I would divide by 0 in the denominator. So I set the denominator, so x to the fourth plus 4 equal to 0. And so if I solve that, I get x to the fourth is equal to minus 4. Minus 4 can be written as 4 times e to the pi I. Okay, e to the pi I is negative 1. That plus k times 2 pi I. Okay, because you can rotate as much time as you want, add as much angles, as much 2 pi I as we want. We will get always at the same place. Okay. So x to the fourth is equal to 4 times e to the pi I plus k times 2 pi I, okay? And so now I can take the fourth square root and I get that x is equal to the square root of 2 times e to the pi I over 4, okay? I take the fourth square root, so it's like all to the power 1/4, okay? So I get pi I over 4 plus k times 2 pi I over 4, so k times pi I over 2, okay? And so now my k is between 0 and 3. Why? Because I have the fourth square root, so I go from 0 to n minus 1, so n minus 1 here is 4 minus 1, so 3, okay? So k is 0, 1, 2, and 3, okay? Now I need to, again, make a differentiation, and I need to I have two cases, when omega is negative and omega is positive. When omega is negative, we will need the counter integral along the circular axis in the upper half plane, and if omega is positive, we need to go along the circular axis in the lower half plane. Why? Well, we will see in a minute, as in the two last videos. Yes, because we need the integral to be convergent. We need an exponential decay, but we'll see that later. Okay, so for the first case, if I use this contour here, I only have two poles in my regions. The poles where k is equal to 0 and k is equal to 1, okay? I don't remember where they are. I think, if I remember well, that one should be like somewhere here and the other one somewhere here, okay? And for k is equal to 2 and 3, that are in my domain when omega is positive, they would be, I think, here and here somewhere. Yes, so for the first case, omega negative, I only have k is equal to 0 and 1 as poles in my regions. So here I am lucky because I have a pole of order 1, okay, it's only to the first power, not squared, or to the third power, or to the fourth power, it's only to the first power in the denominator, okay, it's all to the first power, okay, generally we don't write it if it's to the first power. So I can use my residue formula that if I have a fraction, it's of order 1 in the denominator, well, I simply take the derivative of the thing in the denominator, and the thing in the nominator, they don't change, okay? The thing above the fraction bar, they don't change. So if I take that, so I simply take the derivative of the denominator, I get the following. So on top, nothing has changed. I still have x squared plus 2 times e to the minus I omega x. But in the denominator, the derivative of x to the fourth plus 4, well, 4 is a constant, so it is 0. But x to the fourth, we get 4x to the third power, okay? And so now if I plug in k is equal to 0, so I have no pi of I over 2, okay, that's simply 0 here. I get the square root of 2 times e to the pi over 4. I plug that into my x's here, and I rearrange a bit, and I should get the following, okay? So my negative I times e to the omega 1 minus I over 4. And if I plug k is equal to 1, so I get square root of 2 e to the pi over 4 plus 1 time pi I over 2. And I rearrange that and plug it into my residue here. I should get negative I times e to the omega I plus 1 over 4, okay? Okay, so yeah, now, So we will do a counter integral, so we have the part along the real axis and the part along the circular axis in the upper half plane. So my first part along the real axis, so this first path, well, is simply our original integral, because we go from negative infinity to positive infinity. And our second path, so the circular path, as usual in the last two videos, we already did so. We will let x be equal to r e to the pi I t, where t, this is a t here, is between 0 and 1. Again, why? Because we are in the upper half plane, so we are rotating in this direction, okay? In the other case, t will be between 0 and negative 1, because we are going through the lower half plane, okay? And again, this is because e to the pi I t, okay, e to the pi I t, I mean e to the theta I, more generally, this is a circle, as seen here. And so if you put pi I, and then the t will let it vary between 0 and 1, or 0 and negative 1, we will get a half a circle, okay? If it's between 0 and 1, it should be the upper half circle, and if it's between 0 and negative 1, it will be the lower half circle. And yeah, if it would be between 0 and 2 or 0 and negative 2, we would make an entire circle, sorry, an entire term. Yeah, but that's not the case here. So t is between 0 and 1 here for the first case, and dx is pi r to the pi I t dt. Okay, we just take the derivative of that thing, but that isn't really that important, okay? And now we substitute everything with t, so we get the integral from 0 to 1, because t is between 0 and 1. We can plug in everything. Instead of x, we put the t's, okay, so the r, e, pi I t, and so on. And also the dx can be replaced by the pi I r e to the pi I t dt. But what's really important is that we get our exponential decay, as in the two last video. We want to prove that the second part, so the part along the circular axis, be it around the positive circular axis or the negative circular axis, so in the upper or lower half plane, it doesn't matter. We want an exponential decay, so e to the minus infinity, because we want to prove that this second part vanishes as our radius r gets larger and larger, tends toward infinity, okay? Yeah, and to do that, we need to make sure that the sign of omega and what we are going to get as exponent here in this e, that we need to make sure that you get a negative exponent, so that you get our e to the negative infinity. Okay, the infinity will always be our radius, and it will also always be positive, because a radius cannot be negative. Okay, it's a geometric distance, cannot be negative. And so if our radius is always infinity, tends towards infinity, we need to make sure that everything else gives us something negative, okay? So that we get our e to the negative infinity here. So here we have our e to the minus I omega r e pi I t, okay, so this r pi I t is our x here. And yeah, we can rewrite everything else, but that's not really that important, because we're going to focus on this part here, so on this exponent inside an exponent. Now we know that e to the theta I can be written with Euler's formula, so we know that it's equal to cosine theta plus I sine theta, okay, going to remember that. And so we can write, we have an I here, okay, and we have a negative I omega r e pi t, sorry, not this I here, we have an I here. So we have an e to the pi I t, sorry, not this I here. It will come later. But this I here, so we have e to the pi I t, so we have our I, and our theta will thus be our pi and our t, okay? Everything else that is not your I in here will be our theta. So here it's pi t. So we can rewrite this e to the pi I t as cosine pi t plus I sine pi t, okay? And then we can take our negative I, this time this I here, as said before, this negative I inside, okay? And we let the omega here and our r outside. They are still here, but our negative I is inside. So we multiply our cosine pi t plus I sine pi t by this negative I. And so we get negative I cosine pi t plus negative I times sine pi t, okay? And negative I times I, that is negative I squared, that is negative negative 1, that is simply 1, okay? And so we get just a 1 here in front. We don't really write it, but you could, of course, if you want. So now, as said before, our omega here is assumed to be negative. And we know that the R is going to tend toward infinity because it's the radius. And so, because our omega is already negative, we need to make sure that everything here inside isn't going to have a negative sign too. Okay, otherwise we would get a negative negative, so a positive, and we would get positive infinity, and that's not what you want. You want negative infinity. Okay, an exponential decay. So first we know that even though there is a negative here, this cosine here is bounded. Why? Because there is an I here. Okay, so we get e to the I something. So e to the I theta as before. We get e to the negative I cosine pi t. Okay, so even though there is a negative here, this e to the negative I cosine pi t is bounded, okay, because it's of the form e to the theta I, okay. As long as there's an I inside, we don't care. So the cosine is fine. Now the sine, there is no I inside, so we need to make sure that this thing is really positive because we already have a negative with the omega, okay. So now we know that our sine will always be positive in the upper half plane, okay, because remember the sine is usually along the imaginary axis and the cosine along the real axis. But if our contour integral is along the in the upper half plane, our sine will always be positive. Also, we said that our t is between 0 and 1, and so sine of pi t will always be positive if t is between 0 and 1, okay? Sine of pi t will be negative if t is between 0 and negative 1, but here t is between 0 and 1, so it will always be positive. You can check it, okay? You can plug in, sine of pi over 2. Sine of pi over 2 is 1, okay, so it's positive. Sine of pi over 4 is also positive. It's something real plus something complex, but it's positive, okay? And also the imaginary part, we don't really care. We just need to make sure that we just need to make sure that the sine value basically doesn't give us something negative, because we already have a negative in form of this omega. Yeah, so sine is positive, omega is negative, so we have a negative exponent, and I said our R will go toward infinity, and so we will get e to the negative omega, which will tend towards 0, okay? That's the whole point of the proof part. And we need to prove that the second part along the circular axis between the upper or lower half plane vanishes as our radius goes toward infinity. So we are only left with the part along the real axis, which is our original integral from negative infinity toward infinity, okay? So here, and so we get that we have our original integral, so the part along the real path, plus 0 is equal to 2 pi I times the sum of the residues, okay? So that's all we want. We want to make sure that the second part vanishes, so that the first part, which is our integral, can be set equal to 2 pi I times the sum of the residues, okay? So for the first part, the residues are, as said, here and here. So for k equals 0 and 1. And so we have two residues, as said, for k is equal to 0 and 1 of this whole thing here. K equals 2 and 3 are in the lower half plane for the second case, that we'll see later. And so here, if we take our residue here and set in for our value here for k equals 0 and 1, we get the two residues here, as already said before. And now, so we can plug them in here instead of sum of the residues. We would put these two residues, and now we multiply by 2 pi I, okay? And so we can see that there's an I here and negative I here and here, so we get 1, okay? We get negative I squared, so negative 1, and we get 1 as before here. The same, so it's similar. Okay, now we have our pi here, and then we can factor out our e to the omega, okay, because it is here and here. And then we're left with the e to the negative omega and e to the positive omega over 2, because we have 2 here, 2 pi I, and we have over 4 and over 4 here. So this is, we have this thing here, so e to the minus omega I plus e to the omega I over 2, and that, if you remember well, that is can be written as a cosine, okay? This is one of those strange formula for cosine, and also sine, there is a similar thing for sine, okay? But this here is for cosine, okay? And so yeah, we have for pi e to the omega times our cosine of omega. Okay, and also omega here is assumed as said to be negative. Now for the second part, so if we assume that omega is positive, we need to go around the lower half circle again, because then we want to prove later that the part along the circular axis converges towards 0 as the radius gets larger and larger, and for that we need to make sure that we have a negative sign in the exponent. So if omega here is positive, we need the sign to be negative, and so given that the sign is generally around the imaginary axis, we need a negative imaginary axis. Okay, here the omega is negative, so the sign should be positive to have a negative in the exponent, and so our sign around the imaginary axis should be positive. So here, if we go around the lower half plane, only k is equal to 2 and 3 are inside, so roughly here and here. And we can compute everything with the formula here for the residues and plug that here into those x's with k is equal to 2 and 3. And if you solve that, then solve, you should get 1 over 4i times e to the minus 1 plus I times omega, and 1 over 4i times e to the minus 1 minus I times omega. There's two things. Okay, it's the same thing as before. You take that residue here, you plug in your values for x here, but not for k is equal to 0 and 1, but k is equal to 2 and 3, and you solve. And then again, the proof part is the same thing. That's why I didn't write everything as before. Your part around the real axis is your original integral from negative infinity toward infinity, and for the second part, so the circular axis, you let your x be equal to r e pi t. Okay, so r is the radius that will tend toward infinity, and e to the pi t will represent your half circle if t is between 0 and negative 1 in this case. Okay, because we are going in this sense. Okay, so in this sense it would be 0 to 1, but now we're going in this sense, so it's going to be t is going to be between 0 and negative 1. Okay, everything else is similar. So again, you can plug in your values. The thing that changes is that the integral is not from 0 to 1 like here, but 0 to negative 1 again, because t is now between 0 and negative 1 instead of 0 and 1. So again, you can plug in everything for x's and dx, but you don't really care about it, because the important part is again the e to the minus I omega x. Okay, so e to the minus I omega x is the important part. So again, you plug in your x is equal to r e to the pi t inside this e to the minus I omega x. Okay, and so again you get this e to the omega r times negative I cosine pt plus sine pt as before. Okay, this hasn't changed. But now our omega is positive, so for the whole thing to be negative, again remember that e to the minus I cosine pt is bounded, so we don't really care about it because it's something of the form e to the theta I, which is bounded by definition. We need to make sure that given that our omega is positive, our sine of pt needs to be negative. Okay, as said, that's why we chose this other country, because the sign needs to be negative. Okay, for the first case, omega was negative, so sign should be positive for the whole expression in the exponent to be negative. Here it's the opposite. Okay, sign omega is positive, so sign pt should be negative. And that is in fact the case for, as said, for t between 0 and negative 1. And also, as said, because the sign is generally along the imaginary axis, so if the imaginary axis is entirely negative, well, everything is okay. And that's okay, yeah? So our sign of pt will be negative. And again, our radius is a geometric distance, so it cannot be negative. You cannot have a negative radius. So here the radius will tend toward positive infinity. Okay, it cannot, a radius cannot tend toward a negative number. So it's always positive, and so we get our r, which will tend toward infinity. And so at the end, I said our negative I cosine pt is bounded if it's in the exponent. So e to the minus I cosine pt is bounded, so we don't care about it because it's e to the theta I basically. Or omega is positive, or r is the positive infinity, and our sine pt is negative for all values between 0 and negative 1, okay, for t. And so we get e to the minus infinity, which will tend towards 0. And so again, our second part, along the circular axis here will vanish, and so we can now apply the residue theorem. So our first part along the real axis plus the second part along this circular axis in the lower half plane are equal to our original integral plus 0, as said, because it vanishes. That's what we proved here, and that is equal to negative 2 pi I times the sum of the residues. Why negative? Because as said in the last video, and I forgot it in the first video, but I've written something in the description of this video. We have a negative here because we're going counterclockwise, okay? We go from negative infinity to positive infinity. Let me maybe change color. We go from negative infinity to a positive infinity, and then we go clockwise. Sorry, we go clockwise from positive infinity back to negative infinity through the semicircular axis in the lower half plane. Okay, here it is positive because we go from negative infinity to a positive infinity, and then we go counterclockwise back to the negative infinity through the semicircular axis. Okay, so this is positive. If remember in math, if we have something counterclockwise, that implies that this is positive. If you have something clockwise, that implies that this is negative. There is no true geometrical meaning of that. It's just the mathematician decided that it's like that it works like that, and so everyone followed the rules. Okay, so here I said we are clockwise, so we have a negative in front of the 2 pi I. Here we have a plus in front of it that we don't write, okay, but it's positive because it is counterclockwise. Okay, just remember that, it's very important. Okay, I forgot that in the first video where I had x over x squared plus 1 the whole squared, if I remember well. When I take the Fourier transform of that, I forgot it there, but I wrote it in the description. But here we won't forget it. And yeah, so we will be very careful. There is a negative sign in front of here because it is clockwise. So negative 2 pi I times the sum of the residues. Again, the residues are here and here. Yeah, that were obtained before for k is equal to 2 and 3, okay? And not 1 or 0, but 2 and 3, because they are only those two are only in this region in the lower half plane. And yeah, so we managed to use this residue formula here and this value here for x, for k is equal to 2 and 3, to get those two residues, as in the first part, similarly for the two other cases. And so now we multiply minus 2 pi I by those two residues, okay? So minus 2 pi I times the sum of those two residues. And so now again we can rearrange it, and we get pi e to the minus omega times e to the minus omega I plus e to the omega I over 2, and that is equal to pi e to the minus omega times cosine of omega, like in the first case, okay? So that's the same thing. The only thing that changes is the exponent, but that makes sense because the whole thing here also needs to converge, okay, for values of omega. Here we assumed in the second part that omega is positive, so we have a negative exponent, so it converges. And here in the first part, omega has no negative sign in front of it, but that is because we already assumed that omega is negative. So in fact, you have here a negative exponent, okay? So yeah, so that is an extra way to check if your results seem to make sense. If at the end you have something that seems to converge, then it's already a good sign. If not, you probably made a mistake somewhere, okay? Again, this is only the case if you use the Fourier transform and you use the residue theorem to evaluate the Fourier transform. I don't know in other cases, but for this case with the Fourier transform, generally this is a good sign when there is an exponential decay in your Fourier exponent at the end, okay? Yeah. So again, so for finally, we have our pi e to the omega cosine omega for omega negative, and the pi e to the negative omega times cosine of omega for omega positive, okay? So those are our final results, okay? So that's the end of this video. I hope it was clear and that you could read the majority of what I wrote. Yeah, so the main focus really are, first, if you want to evaluate the Fourier transform using the residue theorem, you find your poles as usual. Here in this case, in comparison to the two last videos, the poles are not that nice. That's why we write this negative for with e to the pi I here plus k times 2 pi, because that is generally the meaning. I mean, in the last two videos, if I remember well, the poles were simply I and negative I. That is clean. But here you can already see that the poles are like here, 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 and here. So it's something with real and imaginary parts, so it's already complicated. So in those cases, it generally makes more sense to use the e to the pi I times k plus k times 2 pi or whatever to show your poles. Okay, so yeah, and then you take the square root. So here's the 4th square root. It could be the 6th square root, the 10th square root, the nth square root. It doesn't matter. Here it's just 4 in the denominator, and so yeah, we get our poles. Okay. Yes. Yeah, and then as said, yeah, we calculate our residues. So for the two different signs of omega, depending on the sign, we have Noether regions. If sign is negative, we do it in the positive, so in the upper half plane. If sign is positive, we do it in the lower half plane. Okay. Again, why? Because we need at the end for the conversions to make sense and to cause the second part along the circular axis to vanish. We want it to disappear. That's why we need to make this case difference. Okay. Yeah, so we find the residues here. Here it's a pole of order 1 in the denominator, hopefully, luckily, so we can just use the this simple formula. So the part above the fraction part doesn't change, the part below we just take the derivative. That wasn't the case in the two last videos because we had a pole of order 2, so we needed to use the formula for poles of order n. But here it's not the case. So we find the residues then, and again, then we can do a counter integral. Here we're going counterclockwise. That's why at the end we have a positive 2 pi I. Here we go here we go clockwise, and here we have a negative sign here. Okay, that's really very important. Okay, so here counterclockwise, so positive, and here clockwise, so negative. Okay, and so now we have our counter integral. So the first part will be as expected our original integral, so from minus infinity toward infinity in both cases. Okay, that doesn't change. And then the second part is the circular axis, and you want it to disappear for a radius that is very, very large. Okay, a radius that is very, very large. Okay, so here in both cases we set our x equal to r to the e pi t, which represents a circle of radius r, and our t will vary between 0 and 1 or 0 and negative 1. Okay, if it would be between 0 and 2 or 0 and negative 2, we would do a whole circle, but here we only have half a circle, so we only do half. So from 0 to 1 or 0 to negative 1. Okay, and so as I said, then you plug in everything in terms of t. Also you have your integral boundaries from 0 to 1 or 0 to negative 1. But the most important point is simply that you get your exponential decay. Okay, you have your e to the minus I omega x here, and instead of x, you plug in your r e to the pi t. Then you use Euler's formula, so e to the theta I is equal to cosine theta plus I sine theta. And you need to make sure that at the end you get an exponential decay, so e to the minus infinity. So you can say that this tends towards 0, so the whole thing vanishes. Okay, that's what we did here in this part. This part here, okay, here we proved that if omega is negative, the sign of pt needs to be positive, because remember the e to the negative I cosine pt is bounded because there's an I here, so we don't care about it, we only care about the sign. And for the second part, it's the same thing, just in the opposite way. If here omega is positive, so the sign should be negative, which is the case if we have a negative imaginary axis. Sign is negative generally. If we do the half circle in the lower half plane, so sign is negative if the imaginary axis is negative, so in the lower half plane, and sign is positive if the imaginary axis is positive, so in the upper half plane. Okay. So sign negative in the lower half plane, sign positive in the upper half plane. Okay. And so that's the case here. So the omega and sine pt should always be of opposite sign, okay, to get your negative exponent. And so you let your radius tend toward infinity, and so you get e to the minus infinity, which will tend towards 0 until the whole thing vanishes, okay. So that's the whole point of the proof. So now you can get rid of this second part along the circular axis, and you're only left with your original integral, which is now equal, according to the residue theorem, to 2 pi I, or negative 2 pi I if you go clockwise, times the sum of the residue. So in both cases you have different residues because there are different poles in the region, but in both cases it's the same. You multiply with 2 pi I or negative 2 pi I with those two residues here that we got in each case, and then you get your final answer. Yeah, and you can rewrite this e to the minus omega I plus e to the omega I over 2 as cosine omega in both cases. And again, at the end, you just need to be sure and write clearly that this result here is only for omega negative and the other one for omega positive. In my exam, they removed points. We lost points if we forget at the end to write that this that the given result is only valid for a given sign of omega. If you forget to write that this given result is only valid for a negative or positive omega, we lost 1 or 2 points, which was a lot in your exams. Yeah, so really be careful. Maybe your professor does the same thing, maybe not, but in both cases it's useful to write it at the end. Also for your comprehension, that you understand what you really did. Okay. Yeah, so that's it. So really the main focus of this video was for us in the last two to show how to prove that the second part of the circular axis circular part vanishes as our radius gets larger and larger. That's really the main point of those videos, to have the case differentiation for omega positive and negative. And also here in this video, and the last one, but not the first one, that if we have a contour integral and we go along clockwise, we have negative 2 pi I, and if we have a contour integral and we go counterclockwise, we have a positive 2 pi I, okay? So negative 2 pi I for clockwise, positive 2 pi I for counterclockwise. It's really important. Yeah, so that's it. So thanks for watching.